Kia ora Year 12 and Year 11. I hope the revision for Level 3 is going well. I just found a couple of really nice surd equations in an ancient algebra textbook, and I thought I would YouTube them for you for some revision. So here they are. They've both got lots of surds, so pause the video and have a go at them, and then I'm going to work through each of them. Okay, so the first one has got this pattern of surds in it. So it's got 3 root x plus root 9x plus 13 minus 13 equals 0. So what we're going to end up doing is squaring some stuff, and it's going to be easiest if I have one surd on each side. So there are different ways that you can do this, but I kept the 9x plus 13 on its own here and added 13 and subtracted 3 root x from both sides. So that's what I ended up with. The next step here is to square both sides, giving me 9x plus 13 equals, right, so squaring this, I'm going to get 169 minus 2 lots of 39, so 78 root x plus 9x, right, so that's from squaring this term here. So that works out quite nicely in this case. I get 13 is equal to 169 minus 78 root x, giving me 78 root x is equal to 150, let's see if I can add 156. Root x is equal to 2, so x is equal to 4. But remember, whenever I do one of these questions, I have to verify that the solution actually works, because bad things can happen when I'm taking the surd, because it means the positive value. So what we have to do now is systematically substitute that back into the original equation. So we've got 3 root x plus this. So we want to verify. On the left-hand side, we've got 3 root 4 plus square root of 36 plus 13 minus 13, which equals 3 times 2 plus root 49, 7 minus 13, and that equals 0 as required. So that's my solution for that one. So that was a pretty easy problem. The next one involves a little bit more work. Let's go back to it up here. Okay, so I've got surds everywhere, and I'm not going to be able to isolate with one on each side. So I'm going to have to get on with it and start squaring both sides. I'm going to leave it as it is and chuck a bracket around this and square the left-hand side and square the right-hand side. So let's move down here and see if we've got enough room. So just rewriting. This is where we're starting from. Right, so just think about your basic quadratic pattern. When I square the left-hand side, I'm going to get x plus 7 for this bit squared, plus x plus 2 for that bit squared, plus 2 times this. And on the right-hand side, I have 6x plus 13. So it's pretty obvious what to do next here. You're going to collect up all your like terms and isolate the surd on the left-hand side. So that gives me 2x plus 9 plus this is equal to 6x plus 13. So 2 root this is equal to 4x plus 4. So I can straight away divide through by 2. Giving me 2x plus 2. Now I'm going to square both sides again. I could factorise out the 2, but I'm not going to bother. I'm going to get 4x squared plus 8x plus 4. Expanding out this side gives me x squared plus 9x plus 14. So we're back to, hopefully, a nicely factorisable quadratic. And we have 0 equals 3x squared minus x minus 10. So if you stare at that for a little bit, or you chuck it into your graphics calculator, this is what we get. We've got 3x here, we want minus 10 here. So let's see if we can get there with 2 and 3. Well, that's not going to work. We're going to have some combination of 5 and 2. We want to have minus x. So I think most of you can do this one by inspection. If you have minus 2 here and plus 5 here, that's going to work out. And we get x is equal to negative 5/3 or 2. But it's crucial here that we verify that it works. So let's go back to the original equation, and it turns out that one of them doesn't work. So the original equation was on the left-hand side, this, and on the right-hand side, this. So if we take x equals 2, this one turns out to be fine, but we have to show it. On the left-hand side, we get the square root of 9 plus the square root of 4, which is equal to 3 plus 2, which is 5. Now on the right-hand side, we've got 6 2s are 12 plus 13, which is the square root of 25, which is 5. So that works. Let's have a look at what goes wrong and how we can show it with negative 5/3. Because it's got some quite nice surd simplification practice. So the left-hand side, I've got negative 5/3 plus 7 plus negative 5/3 plus 2. I think that's right. What do we get here? Is it negative 5/3? Negative 5/3, that's right. So we get, that's right, 16 over 3 square rooted plus 6 over 3, 1/3 square rooted here. So that gives me, splitting that up, now we don't do too much of this, but here I get the square root of 3 on the bottom line, and I get 5 on the top line. Now on the right hand side, what do we have? I know some of you are going to chuck this in your calculator, and I guess that's okay, but it's quite nice doing it with exact values. So we get the square root of 6x plus 13 gives me negative 30 over 3 plus 13 over 3, or 39 over 3, which gives me square root of 9/3, which is 3 on root 3, which is not equal to 5 on root 3. So we have to reject x equals negative 5/3 as a solution. So if you've watched this far, you're going to get a chocolate fish for the first person to answer this question. Where did this question come from? Well, it came from a really beautiful old algebra book that we found when we were cleaning up the maths office. In fact, we found a whole class set of them, and they come from 1912, and the author is a Mr. or Dr. H.S. Hall, and it's called A School Algebra. And if you're doing scholarship calc next year with us, you can look forward to lots of cool algebra questions from this book. Okay, and I've got a bag of Freddo frogs in my desk, so I really promise that you really will get chocolate if you've watched this far and you come in and you tell me who wrote the algebra question. Okay, no cheating. Thanks for watching.